Okay, we are setting up the live stream on YouTube, and I will be transitioning to the conference room. Okay. Good morning, everyone, and welcome to our Queens Borough President Land Use Public Hearing. This hearing is taking place both in person in the Borough President's Conference Room and on our YouTube channel, which is searchable by Queens BP. I am Vicki Garvey. I am the Land Use Director for Borough President Donovan Richards, and I will be chairing this hearing on his behalf. For those who wish to testify virtually and haven't already pre-registered to do so, please visit our website at queensbp.nyc.gov. Written testimony is welcome from those who are unable to testify in real time, but all written testimony must be received by 5 p.m. today and be submitted by email to planning2@queensbp.nyc.gov. Lisa, please review how this public hearing will proceed.
Good morning. The public hearing shall be conducted in the following manner. The applicant will give a description of the requested zoning actions, the proposed project, and respond to any questions from the chair. The floor will then be open for public speakers. Please listen for your name to be called. Each speaker will have 3 minutes to ask questions or deliver testimony. When you are called, please identify yourself for the record, and if you are formally speaking as a representative or member of a group, the calendar number and application you are speaking about, and whether you are for or against the item. Then you may begin your testimony. Please note that a signal will ring when your time is up. At the discretion of the chair, if there are a large number of speakers on any particular item, it may be put on second call. Speakers for and against the item will be called to testify on an alternating basis. Please note that if you are testifying virtually, you must keep your camera on during your testimony and display your name accurately on Zoom. Thank you for your cooperation.
Thank you, Lisa. The chair reserves the right to ask speakers for clarifications or further information regarding the applications or comments. So with that, Lisa, if you could call the two calendar items which are related.
Yes. Calendar item number 1 and 2, ULURPS number 250323MMQ, and ULURP number 250324 PCQ. The applicant is the New York City Department of Environmental Protection and the New York City Department of Administrative Services. Affected Community Board number 7. Applicant, please begin.
Alfonso, are you there? Okay, then I will begin for Alfonso. My name is
Hear me?
Angela. Sorry, go ahead, Alfonso.
Sorry, my mute was acting up. Good morning. This is Alfonso Lopez, Queens Commissioner for DEP. Thank you all for the time today. Just going to go through briefly who's here on the line from DEP. Introduce myself. We also have Monica Harvey, Bureau of Engineering, Design, and Construction. Angela Licata, our Deputy Commissioner for Sustainability. Mitchell Wimbish, Bureau of Environmental Planning and Analysis. Keith Mahoney, Bureau of Sustainability. From Arcadis of New York, we have Timothy McDonald. And from AKRF, we have Carrie Sibeli. I'm going to turn it over to our Deputy Commissioner, Angela Licata.
All right, thank you very much for the introduction. We wanted to give a brief outline today to talk a little bit about the project purpose, our objectives, talk a little bit about how we have designed this project and provide you with some of the data that we have collected and studied. We will provide you with the analysis for the environmental documents and provide you with our conclusions. And then we will review the schedule for this project for its ongoing design and for its construction. Next slide, please. So first, a little bit about DEP. Most of you will know that we are the city's agency responsible for providing drinking water services to over 8.25 million people within the city, another million people upstate in our watershed. And we also are responsible for distributing that clean, potable drinking water and collecting all of the wastewater. And that includes stormwater and sanitary sewage. And approximately 60% of the city's sewer system is what is known as a stormwater and the sanitary flow mixed together in one pipe. So again, I said 60% of the sewer sheds are combined, probably another 30 or so are separated, where you have one sanitary pipe and another stormwater pipe, and about 10% run directly into the city's water bodies. The problem with combined sewers, and this is a legacy problem in a lot of older cities, is that when it rains of a sufficient amount, that system does not carry that flow all the way to our water resource recovery facilities for treatment. The city has 14 water resource recovery facilities, but when the flow exceeds 2 times their dry weather capacity, we have what are known as combined sewer overflows. The city has a policy of abating combined sewer overflows, and we have been trying and really struggling. It's a big challenge to eliminate them entirely. And so that's why this is a program that has been ongoing since the 1990s. We've made tremendous progress, and I think most of you have witnessed and heard about the tremendous recovery in water quality around the city. We now see the return of a richer and more diverse habitat, which is allowed for dolphins and whales, and those type of marine mammals to prosper. But more can be done and more should be done, and that is the trajectory that we are on. Okay, next slide, please. So we have a consent order with the New York State DEC, and we are governed under the Clean Water Act. That's a federal policy. And what we need to do is to meet a series of best management practices, is what they're called. We want to continue to improve our water bodies until they can all meet a swimmable, fishable standard. Now, having said that, that's a very difficult task to achieve because New York City is blessed with 520 miles of coastline, and our water bodies are vast, and we're really an archipelago. So we have a lot of water bodies to manage, and some of these water bodies are really quite man-made. And so getting them to achieve like you would see in an ocean fronting beach where it can meet a swimmable, fishable standard is again really quite challenging. But nevertheless, we have been developing programs to get us closer and closer to these goals. And that is why we have proposed for Flushing Creek a disinfection program. Typically, under our CSO program, what we try to do is capture that CSO, detain it, store it, pump it back to one of those water resource recovery facilities that I spoke about earlier once the rain event subsides. But in some cases, like in the case of Flushing Creek, that is a very difficult thing because we have over 1 billion gallons of CSO going into Flushing Creek every year. And so a tunnel like we are proposing in Newtown Creek would be quite massive and is really above and beyond, I think, any tunnel that anybody has done. So just to give you an order of magnitude, the tunnel for Newtown Creek, which we consider very large, is about 50 million gallons. In order to get an equivalent disinfection that we're proposing for Flushing Creek, we would need a tunnel of over 200 million gallons. That's probably not practical and achievable in the city's environment. Would take decades and multiple billions of dollars for us to accomplish. So and I'm going to turn it over to Keith, who's going to go through the decision-making matrix that we utilize when we cannot do storage, when we cannot do detention, when we cannot do pump back to the treatment plant. The next best bacterial loads, which is what occurs in these combined sewer systems when you're mixing the sanitary with the stormwater, we propose a disinfection plan. So next slide, please.
Okay, thanks, Angela. So as Angela mentioned, the CSO program has a long history. It started back in the 1990s, and there were a lot of accomplishments to date. In Flushing Creek was one of the largest ones. We constructed a 43 million gallon CSO retention facility just upstream of CSO outflow TI-10. So that's a massive CSO storage facility. But even with that storage facility, there's still over a billion gallons going into Flushing Creek. Their previous was 2 billion gallons over going in. So we significantly reduced the CSOs. But again, it becomes very challenging to try to reduce that remaining 1+ billion gallons. Aside from that, we also have a very comprehensive green infrastructure program, and there's a lot of green infrastructure in this area. It's a huge sewer shed upstream of Flushing Creek, and to date, DEP has constructed over 2,000 GI assets in this drainage area, and we continue to implement more GI. And citywide, we call this kind of our baseline CSO commitments. This is prior to the long-term control plans. We've already spent over 2.7 billion in gray infrastructure, and we've committed to spend 3.5 billion in green infrastructure throughout the city. We also made other improvements in this area, including some sewer upgrades, and we constructed a new parallel interceptor to convey more wet weather flow to the Tolman Island treatment plant. So again, a lot of investments have been made to date in this area, but again, it's still a challenging area. Next slide, please. So as part of our 2012 consent order, we were required to develop what we call CSO long-term control plans. And we submitted 11 of these citywide. All 11 have been approved by DEC. And in this, we look at what we can do beyond what we've already committed to. So it builds off of that 43 million gallon tank and the GI we committed to. So this is what's in the future, what we can commit to. So as part of this, we call this kind of a toolbox, but there's a whole different list of alternatives we can look at, including disinfection, which was actually required by our regulators, New York State DEC, to be included in the toolbox. So we have a lot of system optimization, like some low-cost things that were done previously, and those are much more cost-effective things. As you start going down this list of storage, it becomes very expensive, as Angela mentioned. For instance, the Newtown Creek, that 50 million gallon CSO storage tunnel, has a cost right now of $3.4 billion. So it becomes very expensive. So again, when we have these alternatives, what it's called the near the curve analysis. It's basically a cost benefit analysis. So we looked at all these alternatives and saw how they reduce CSO, reduce bacterial loadings, and most importantly, we did an evaluation of how they improved water quality attainment with the applicable bacterial standard. So based on that, we kind of selected the most cost-effective alternatives for each water body. It just so happened in Flushing Creek, disinfection was by far the most cost-effective. And that's kind of how we came up with disinfection. So as part of this project, we have floatable control, disinfection and a long outfall, as well as disinfection the existing 43 million gallon tank. And another project that we committed to outside of the long-term control plan was a wetland restoration that we're doing with the Army Corps of Engineers. So that's a project I'll get into in the next slide. So these are some ongoing or planned improvements for Flushing Creek. Again, I just mentioned the Flushing Creek wetland restoration. So we're looking to construct 19 acres of habitat included including taking out some invasive vegetation, some regrading, placement of clean cover in the creek to grow the new plantings. In terms of, I mentioned the GI we already constructed, we're also committed to additional GI as well as cloudburst management program. So this is kind of a hybrid of GI with storm sewers, roadway improvement. It's really meant to help mitigate inland flooding, but it also has a CSO reduction benefit. So we're pursuing these citywide to try to address climate change and increase precipitation. We also have ongoing throughout the city sewer separation projects. As Angela said, the city, about 60% is combined. It's almost impossible to make it all separate, but there are pockets where we have opportunities to separate sewers. And we're looking at some within the Flushing Creek area where we'll take some pockets of sewers, separate them, and send the additional flow to either Meadow or Willow Lake. So that gets the stormwater out of the combined system, but again, incrementally. And I did mention this early green infrastructure program. Again, we're doing this citywide with we committed to spending $3.5 billion by 2040. And to date, I think we probably spent about $1.3 billion or so. This is just a timeline for the long-term control plan. As I mentioned, the CSO programs from the 1990s. We started the LTCPs back in 2012 with the amended consent order. We submitted to Flushing Bay in December 2014. Had a public engagement. We had 3 public meetings for every LTCP to discuss the whole process and the alternative evaluation and the recommended alternative. DEC approved the Flushing Creek, in March 2017. We started design for this disinfection project in January 2019. And we're approaching design completion. And right now we're in that process where we're reaching out now to the borough president and looking to get the lands and just proceed with this project. The next phase is construction coming up. And I'll hand this one over to Mitchell. Thank you.
Thanks, Keith. All right, so for this project, as we've been talking about with this disinfection, so CSO is going to be chlorinated to kill the harmful bacteria and viruses that are in the CSO effluent. And then another chemical will be added to dechlorinate the flow to protect the ecosystem of Flushing Creek. And we are designing this amount of chlorine in the effluent, and we have a limit of 0.1 milligram per liter. That's what the DEC's limit that we have to meet all the time in order to protect human health and safety during recreational uses. So we're looking to construct 2 facilities. So on this map, at the top of the map, the triangles are the outfalls. So that's TI-11 at the top, and then TI-10 at the bottom. And so for TI-11 at the top, we're looking to construct a new facility on 32nd Avenue, right below the Whitestone Expressway. That's a current traffic triangle owned by State DOT. And then for TI-10, we'll actually do the chlorination within the CSO facility that's here in purple on the map. And then the dechlor will be in our new building on Avery Avenue. And that is a portion of a lot owned by the Home Depot that we will look to acquire once we have approval. Next slide, we'll just go through the ULURP actions like I'm talking about. So we can see a little closer here. So for both sites, we need to site select and acquire. And then for the TI-11 site on the top, we have to a mapping action because it is currently mapped roadway, part of the Whitestone Expressway access road. So we need to change the city map so that we can build, make a new lot to build on. And then you can see below, we're just acquiring a portion of the Home Depot lot. The Home Depot store is on the right-hand side of the screen in the blue area, and we're just acquiring the red portion of it. Next slide, we'll just look at the surrounding land use. This is for TI-11. This is the traffic triangle under the Whitestone Expressway. You can see it's almost all manufacturing uses around it with the highway right above it. And then for TI-10, we are right next to Flushing Meadows Park. And then the red is the Home Depot facility. And then, so just to give you the view, this is the TI-11. So this is the traffic triangle. See there on the bottom. It's behind a fence currently, and just right under the Whitestone Expressway. And then the next slide has our site plan for TI-11 and just shows how the trucks for maintenance and supply delivery will enter and exit the site. And here's a rendering of what it'll look like. And then let's move on to TI-10. So this grassy area on the bottom, the left-hand side of the picture on the bottom shows the grassy area where we would construct our facility. It's currently pretty isolated, so it's on the other side of the Van Wyck Expressway from the rest of the Home Depot property. And this is actually East Road that goes into Flushing Meadows Park that you're looking at. And then the next slide has another site plan, just again showing you the way the trucks would enter and exit the site, and then another rendering showing this one also right under the Van Wyck. And then I think, yeah, Tim, go through some of the modeling and design elements.
Yep, thank you, Mitch. So Arcadis picked up where essentially Keith's team with the long-term control plan finished off. And it's our responsibility to now come up with the physical design of the new facilities and to figure out how they're going to be implemented and constructed to achieve the project goals. So to do that, one of the first things we did was we revisited some of the sewer system modeling that the long-term control plan team had looked at. And we built upon that and basically enhanced it to take into consider future projections of population and then also what's happening in our environment with climate change. So what you see on the right here, this is a map of the entire sewer shed area for the two Flushing Creek outfalls that we're talking about today. That's highlighted in the red area within the map. And then the colors represent, the green represents the combined sewer areas and the blue represents the separated sewer areas. So as you can see within that red outline, there's still quite a bit of area that is considered combined. And so what we do is we use modeling, we use sewer shed hydrologic and hydraulic modeling to take a look at when it rains, what happens within that red area. Where does the rainfall go? What catch basins does it go into? What sewers does it get into? How much of it collects in the sewer system during some of these wet weather events? And how quickly does that water move through the sewer network and out to the outfalls? And also, how much gets to the two outfalls that we're concerned with for TI-10 and TI-11? We also use another modeling software known as computational fluid dynamics, or what's referred to as CFD modeling. And that looks at once the water's inside the sewer conduits and the sewer pipes, what happens in there? What are the mixing characteristics? What happens when we add chemical? How do we assure we evenly distribute that chemical throughout the water column and get it in contact with the CSO? And we can also use that to get an idea of how much dilution occurs, so whereby as we get to the outfall pipe, we ensure that we're below the limit that the state allows for residual chlorine in the water that does go out to Flushing Creek. Okay, and ultimately in looking at this whole sewer network and looking at the two pipes, how much chemical gets added, we're able to determine the percent disinfection of the CSO flow that goes out to Flushing Creek. Next slide. So using that modeling data, we get a sense of what happens during a recreation season. So the table here shows at a very high level for the two outfalls. The top row is for TI-10, the bottom row is for TI-11. How many overflow events occur during the recreation season that result in water going out to Flushing Creek? So for TI-10, it's about 8 events in that recreation season period, which is from May to October of every year. For TI-11, it's about 23 events. The reason being it's higher there is that in TI-10, we have the Flushing Bay CSO retention facility, the big tank, the 28 million gallons of storage that Keith referred to, that helps mitigate the amount of events that would actually overflow to the creek. From a durational perspective, this just shows the total duration during their recreation season for when these overflow events occur. On average, it's about 16 to 18 hours per event. Some of them are shorter, some of them are longer, depending on the rainfall intensity and the duration of the storms. As Keith mentioned as well, it's about 1.3 billion gallons of water that goes to the outfalls. for CSO overflows. In the TI-10 system, the TI-11 system, it's much less. It's only about 222 million gallons. So when we look at where we're adding the chemical and where we're targeting, we get a sense of how much we're able to disinfect. And in both cases, for both outfalls, we believe we can achieve about 91% disinfection of the CSO flows that are going to the creek. And in both cases, that exceeds the target that New York State DEC identified in the long-term control plan, which was to achieve 88% disinfection of those flows. And then just for comparison here, we also have a couple columns there where we call volume of disinfectant added and the dechlorination agent. And you can see the amount of chemical that gets added in relation to the amount of CSO flow that goes out to the outfalls is very low. It's orders of scale less than what goes out in terms of total stormwater flow. Next slide. So just to give some understanding of how the system operates and why these facilities are being sited where they are. So what we have here on the screen, this is an aerial view of the TI-10 sewershed area closest to Flushing Creek. So the creek's in the upper left. Outfall TI-10 is in the red triangle. And then the blue shading there, that represents the sewer conduit and the sewer network that goes to that outfall. So as you come back, you've got sewers that go down Avery Avenue and Fowler Avenue over to College Point Boulevard. The bottom center of the screen, the big blue area, that's the existing Flushing Bay CSO retention facility tank. So the water in the sewer shed comes from two sets of conduits, which are in the right-hand corner of the screen. There's a larger conduit that comes from the Casino corridor that runs under the Queens Botanical Garden, and then another pipe that comes from what's called the Park Drive East sewer that goes up College Point Boulevard. So normally what happens is these flows get conveyed to the Tallman Island wastewater resource recovery facility. And then in wet weather events, when the flow is too much for the treatment plant to handle, the flow starts to back up in the sewer network and it's directed into the CSO retention facility tank. And the idea being that we capture that flow in the tank, and when there's capacity and treatment availability at the Tallman Island plant, the flow that gets captured in that tank gets pumped back to Tallman Island. But there's times when the wet weather events are so severe that we fill up the tank and can cause an overflow that can go out to Flushing Creek, or they can bypass that facility over on the upper right of the screen there, where it says DC5. That's called diversion chamber 5. So within the sewer, there's a structure that's got gates that block off the flow that normally push the flow into the tank. Those gates can be overtopped or they can be opened to relieve any backups in the upstream sewer system, and then that would allow the flow to go directly out to Flushing Creek. So the diamonds, the red diamonds that you see there on the screen, those are sensors that we're going to install in the sewer network. That's what we'll use to detect when a CSO event is about to occur and when flow is going to go out to the creek. And that would signal a control system to start the pumping of the hypochlorite chemical to the injection points, which are there in the yellow circles, into the sewer network. And then we have additional sensors. So the yellow stars, those are residual chlorine analyzers. And what those are doing is they're going to detect how much residual chlorine is remaining in the water after it's been treated with hypochlorite. And that sends a signal to another set of chemicals to inject sodium bisulfite into the system. And that's the dechlorination agent. So what that would do is it would react with any remaining hypochlorite that could be in the sewer system before that flow gets out to Flushing Creek to make sure that we are down below the limit that the DEC is allowing. Okay, next slide. So here's the TI-11 system. It's a little simpler. The big difference being that there's not a retention tank. So on the right-hand side of the page under Linden Place is the sewer that up to the Tallman Island Water Resource Recovery Facility. And so when can't handle all the flow, there's a regulator that's called TI-RO9 that's at the intersection of Linden Place and 32nd Avenue. The flow would overflow at that location into the sewer outfall pipes that go out to outfall TI-11 into the creek. There's also flow coming in from the right-hand side of the page from some other upstream regulators. So that's an overflow. When we see that it's about to occur, it's occurring, hypochlorite would get injected just downstream of that regulator into the two sewers that then go down the length of 32nd Avenue. And then right about the intersection of College Point Boulevard, that's where we have those total residual chlorine analyzers to trigger and adjust the dosing of the sodium bisulfite to, again, make sure that we don't exceed the effluent chlorine, residual chlorine limit that the state has imposed. Okay, so that's the reason for putting that in the adjacent intersection there to house both chemicals, because this is a very congested area and there's not a lot of opportunity here for constructing new facilities. Next slide. So in the course of development of the project and also some of the various public outreach that we had, the DP has conducted, right, there's been a lot of concern expressed from a safety perspective and the control of the chemical and making sure that there's not any negative impact to the aquatic biota in Flushing Creek. And DEP is concerned with that. And so as part of this project, we've put in a control system and designed a system whereby we've done all of that modeling that I mentioned earlier with the CFD, and then coming up with a robust control system that's based on the same types of equipment and controls that the DEP uses at all of its treatment plants. So it's tried and true technology that's being applied to this case. And so what typically happens is at the dosing point, what we're showing here schematically at the top of the page is a of the outfall pipes in the sewer network that goes out to Flushing Creek. And at the bottom is what's happening chemically. So at our hypodosing point for the sodium hypochlorite, which is on the left-hand side of the page, that's where we would be adding chemical. And what happens is as the chemical's added to the CSO flow, there's an initial uptake immediately by all of the bacteria and the enterococcus that's in that CSO flow that starts to react with that hypochlorite. Okay, there's also some natural decay that occurs. And as that flow continues through the pipe, that uptake continues to happen and the decay continues to happen until we get to the point just upstream, well upstream actually, of the actual outfall pipe. And if there is any residual chlorine remaining that has not been taken up by the bacteria that's in the CSO, that's where we would add the sodium bisulfite to further react with the hypochlorite. And that reaction's fairly instantaneous. We have good mixing in the pipe at the locations that we're adding the chemicals. So we anticipate that once that's added, if there was any residual chlorine prior to the outfall, that we'd actually be able to remove whatever's remaining there and get below, in most cases, the limit that the state has imposed. But in all cases, we would be under that limit as part of the design and the operation of the facility. Next slide. And then with respect to public safety, there's been a lot of concern because we do have some buried piping that has to extend outside of the DEP's fence lines and into the right-of-ways to get out to the various locations within the sewer network. So the piping that's going to carry the chemical, normally we would have what's called a double contained pipe. So basically you have a carrier pipe that carries the chemical, and that's surrounded by a secondary pipe around that. And that would capture any material that might leak inadvertently out of that pipe. And then in the annular space between those two areas, we have a continuous leakage detection cable that runs the entire length of the pipeline. So if any chemical did leak out of that pipe, we could detect that, we get an alarm, and we shut down the system. It also can tell the operators to within 5 feet as to where that leak may have occurred, so they can go out and investigate it. In this case, since we're in the public right-of-ways, we're taking that double contained pipe and we're going to put it in a concrete trench box that will act as a triple containment. That trench box that's shown there in the graphic on the left, that would also contain any of the signal wiring or electrical cables or any of the sampling pipes that we need for operation of the system. And then above that, we would cover that with a steel plate and then detectable warning tape. So if anyone did dig in the right of way and wasn't aware of the location of the pipe, it's adequately protected so that we prevent anyone from inadvertently breaking it during construction activities. Within the facilities themselves, There's a lot of containment provisions. So there's a schematic here in the lower right of the tanks and the pumps. So every chemical tank has full redundancy. The tanks themselves and the pumps and all the piping sit within a containment area within each facility that gets monitored as well for leakage. And then all of the controls for these facilities are generally automated. They come with full redundancy and backups in case any of the sensors or the control systems were to fail. So there's continued operation. And then the final fail-safe is operator intervention. Everything's monitored remotely by the DEP, and chances are, in most cases, when the facilities are activated, at some point after the activation, the operators will come to the facility and they'll do manual checks of everything to make sure everything's operating correctly. Next slide. Okay, and I'll turn it back to, I guess, Mitchell on the AS conclusions, because I think Angela had to drop off.
Yeah, thanks, Tim. Angela, if you're still here and want to jump in, please do so. But yeah, so we released our EAS in September of this year, and then had no comments received on it, and we issued a neg deck on October 1st. And there were no, so therefore no significant adverse impacts were identified in any category. And then we just talk a little bit, if you go to the next slide, we'll talk a little bit about our analysis on natural resources. You know, as Tim mentioned, you know, we did this very detailed modeling work to really determine the minimum required dosing rates to achieve disinfection, because we did want to minimize the amount of chemical use. And we know that, you know, any chlorine that's still in the water does have the potential to be harmful. So that's why we're using both the design to have that be the minimum amount necessary, and then also using the sodium bisulfite to remove any remaining chlorine. And as talked about before, we have both the analyzers to tell us how much chlorine is in the water and flow meters, and those are all giving real-time data to the operators so that we can adjust you know, the dosing as storm events are happening. And this, we looked at other places where this dechlorination process is used, and in places like Seattle that has wet weather treatment stations that they disinfect and dechlorinate CSO flows that don't go to a traditional treatment facility. And we also know that DEC has permitted this in several other places throughout the state. And often, you know, ours will have a lower allowed limit, that 0.1 milligram per liter of total residual chlorine. That's a lower limit than a lot of the other facilities using. And also, you know, DEP has so much experience using chlorination and dechlorination at our treatment facilities, which are run 24/7. And we see we do have more of a higher limit there where we can, that we put into the receiving waters, and we haven't seen you know, real problems with the aquatic life. And then just highlight, so this, it's, I don't know if we talked about this before, this disinfection would only be happening during the recreational season, which is May 1st through October 31st. And that's really to highlight the benefits of this project are to remove those dangerous pathogens and viruses that are in CSO, so that people who are near the creek wouldn't become sick due to exposure to those pathogens. And so, you know, these all kinds of things were put into our determination that this would not have a significant adverse impact to the natural resources. And here we are. So the schedule on the screen now, as mentioned, we did the neg deck in October, and we certified, and we're now going through the ULURP process. We've completed the community board and looking to complete ULURP in May, and then hopefully move into the property acquisition to be done by November of 2026. And then we're looking at a almost 3-year construction period from November, starting in November of 2026 and finishing in 2029. I think that's our last slide. Oh, we have a summary. So yeah, just to go over this again, all the work that Keith and Angela mentioned on our LTCP, we've been working on reducing CSO into Flushing Creek and all the other water bodies for many years. And we have determined that this disinfection project is the alternative that makes the most sense for this location. And this will achieve 91% reduction in the bacterial load during the recreational season. And yeah, our negative declaration again was issued in October, and we didn't see any adverse effects related to land use and the surrounding properties. And so we're here for the ULURP approval process. And I think that's it.
Okay, thank you so much, applicant team. That was a very comprehensive presentation, a lot of information to kind of parse through, but I appreciate it. And I appreciate that this long-term control plan has been in the making for a very long time. So I do have some follow-up questions as they relate to, well, my first question is sort of an overarching question that I think you did touch on, but I do just want to point out. So this disinfection facility will treat the water, but it doesn't seem there's no plan to address the fact that billions of gallons of CSO will still enter the creek, which will include trash, physical trash. And so I wanted to excuse the noise if you can hear it. I apologize. There's the wind coming through our window. I just wanted to ask, is there any precautions or plans to deal with physical debris that might get into the creek?
Do have another project that's a floatables control project that Keith, I don't know if you know about that more, but
Sure. Yeah. So for these two outfalls, there was previous floatable controls. So the tank itself, there's both an underflow baffle and a bar screen. But there's another project. It's currently in construction. Should be completed shortly, and it's to put floatable controls upstream of the regulators in both TI-10 and TI-11. So we are looking to address floatables, and the consent order date for that is December. There was some 2025. There's a few little delays, but that should be in place next year, those floatable controls. And that'll be upstream of these disinfection injection points.
Okay, understood. That's good to know. I think you might have also touched on this, but just to confirm, so the actual the chlorination and then the dechlorination, how does that work in terms of how much time passes between when the water is chlorinated and when it's dechlorinated? Is it instantaneous? Is it a couple minutes? Just wanted to understand more about that particular piece.
Sure, I can handle that. So from the modeling, the time frames will of course vary depending on the size of the storm, the flow rate, and the duration or intensity of a storm. But from a worst case scenario, when we look at peak flow rate through the system and low tide in the creek, which is the shortest amount of time that the CSO flow would be in the pipe, we have a minimum of at least 6 minutes. And typically the durations are higher. So, and that's the case for the TI-11 outfall because there's no tank and the pipe is shorter length than for TI-10. TI-10's duration is generally higher. It's usually on the order of 10 to 13 minutes minimum. And then it would be longer if you have a high tide or if you have a lower intensity rainfall event that doesn't result in such a high flow rate.
And just to
Okay,
add,
and
okay, I'm sorry, I was going to
go
add
ahead.
what Tim said. For the chlorination, that's where you kill the bacteria. That one is dependent both on chlorine concentration and detention time. So they call it CT. So that one's dependent, and that's why we try to get as much detention time as you can in the outfall pipe. The sodium bisulfite, which is added to take out the residual chlorine, is instantaneous. So that's towards the end of the pipe, and that's a pretty much instantaneous reaction.
Correct. And just to add to that, so after the bisulfite's added, at worst case, which is minimum time in the pipe again, we have around 2.5 to 3 minutes between when the bisulfite gets added before that water gets to the end of the outfall pipe. So at other times, the duration could be longer. Again, it depends on the flow rate going through the system.
Got it. Excuse me. So in layman's terms, I'm not an engineer, so excuse me. So it just to understand the stages, so the chlorine is added to the water, and then as it moves through the pipe, the bisulfate, the sodium bisulfate is added. And so before it reaches the creek, there are these TRC analyzers that read the amount of chlorine in the water that then allow it to pass into the creek if it's under the limit. Is that right?
Correct. So what we do is after we've added the hypochlorite and now the treated water is moving through the sewer network, there's two sets of total residual chlorine analyzers. There's one upstream of where we add the sodium bisulfite. So what that analyzer does is it tells us how much residual chlorine is remaining, and the control system will do a real-time calculation to figure out how much bisulfite should be added to react with that remaining chlorine to get it down to 0 or below the limit that the state has imposed. Okay, then there's a second residual chlorine analyzer that's downstream of the bisulfite addition point that then would measure if there's any remaining residual chlorine in the system before it goes out to the creek. And that signal can also be used to tell the system, hey, we're not adding enough bisulfite, you need to add more. Or if there is, there's 0 residual chlorine, it can also fine tune the system to reduce the amount of bisulfite added. Right, it's basically optimizing the system, but reacting in real time to what's happening in the pipeline. Okay.
Understood. And so as you went through the backup systems and spoke about the, automated with redundancy, the final fail safes, does that plan or that modeling include, the event of superstorms or hurricanes that we might encounter in the next, decade or so?
Sure. The modeling looks at increases in rainfall intensity and duration in events. And essentially what it means for the system is that if you have larger storms and they're more frequent, you're going to use chemical more often. And it would ultimately mean you might have to fill up the tanks more often during a recreation season, as compared to what happens when the system starts up, if that ends up being the case. There's significant amount of excess storage in the tankage available that we're providing in these facilities versus what gets used in a typical peak wet weather event. Okay.
All right, thank you. And then my last question, so you spoke about future green infrastructure here. And so by factoring in future green infrastructure, approximately how many million gallons are you expected to have reduced within the CSO by adding this green infrastructure?
Yeah, we don't have that number quantified, but it's probably talking tens of millions of gallons. So it's just a portion of the flow still going in. But yeah, we don't have those exact numbers. But typically, you'd be looking at tens of millions of gallons of reduction per year.
Okay. All right. So I think with that, we're going to move on to public testimony. Sola, can you confirm if anyone is on the Zoom that would like to publicly testify?
There are no speakers.
Okay. So there are no speakers on Zoom, and I do not see any speakers here. Actually, our director of topography, Mohammed Sadiq, does have one question.
Hi, good morning. This is Mohammed Sadiq, Director of Topography. We are involved with the demappings. So I want to make sure after that you're going to be create block and lot numbers. Since you got this property from a state, but the local street are under New York City DOT since you are in the design stage, the construction. So make sure the coordination is very important with the traffic analysis and other stuffs. Thank you.
Yep, thank you, Mohammed, and thank you for your help and your department's help in the project. So the plan is to go get block and lot numbers, and we have been actively coordinating with New York City DOT in regards to traffic impacts and analysis and construction stipulations.
Thank you. So seeing that there are no other public speakers on these items, the hearing is closed. So thank you, applicant team, for your presentation. Our next scheduled hybrid land use public hearing is in the new year on Thursday, January 8th, 2026, starting at 9:30 a.m. Thank you again, everyone, for joining us, and have a nice weekend.
Thank you. Happy holidays.
Yeah, thanks
Thank you.
everyone. Happy
Happy
holidays.
holidays.